Great, thanks so much, Jake. Let's see, I'll just share my slides here. There we go. Can you see those okay?
Looks nice.
Great. Okay, I'll get started. Thanks everyone for joining us today. Today we're going to talk a little bit about three sort of software pillars that the SESIC group, the Sustainable Energy Systems Integration and Transitions group here at ICEFIC, has been developing to sort of close the gap that we see in what we're calling an effective dialogue around energy systems integration. So the objective of the group is really twofold. The first part is to model the electrification and integration of our energy systems, really from an exploratory perspective, to try to explore different pathways around decarbonization. The second part of the objective is perhaps a little bit more practical, is to try to make sure that that exploration is leading to insights that bring about effective decarbonization actions. And to do this, what we see is really important is being able to deliver relevant and impactful insights to the decision makers who actually have the power to turn those insights into actions. So really what our argument here is that electrification is really a transition that demands a holistic perspective. We need to be able to understand the interaction between infrastructure systems and spatial temporal resolutions sort of in concert as a holistic perspective. But our challenge is that modeling efforts so far have been relatively siloed. So we have, reams and reams of building system models and transport system models and power system models that I think many of us on the call, work on a day-to-day basis. But our issue is that these models and these don't actually connect to one another, typically, don't really link to one another. Let alone linking these kinds of engineering models to, economic equilibrium models that are being run across campus. And this disaggregated approach to the modeling landscape, I think, is really limiting our understanding of electrification, which is inherently a multi-scale and multi-system transition. So as we enter what I really see as sort of the next phase along the decarbonization pathway, which I think is electrification or more broadly speaking, energy systems integration, and as electrification and energy systems decarbonization really becomes one of the key drivers of decarbonization, this limitation of not being able to see a holistic perspective, I think is hugely problematic. So first, let's take a look at how electrification is really a multi-scale transition, both politically as well as physically. And to do this, I'm gonna just walk you through the example of the electric vehicle, which I think is a good sort of case study for looking at this multi-sector perspective. So if we think about the electric vehicle, we think at the municipal scale, we've got planners who are tasked with determining where to put EV chargers, where to site these EV chargers, which inherently demands a fine spatial and temporal scale. We need to be able to look at road networks, where those link up with distribution networks, and this is really at the building level or at the sort of city block level. Meanwhile, we have utilities in the Canadian system who sit at the provincial scale, who are going to need to determine if extra capacity is going to be needed from facilities like Site C, for example, in order to supply these new loads. And this really demands an operational and design perspective, which sits sort of at that provincial or transmission level. Meanwhile, we have policymakers at the federal level who are responsible for coming up with carbon targets and commitments, which then go into international climate agreements. So the result is that our models need to deliver insights not only at each of these scales individually, but also we need to be able to pass insights from one scale to the next in order to be able to sort of link up all of these perspectives into sort of one. And examining any one of these issues at a single scale without understanding the effects on other scales leaves us with an incomplete picture that I think can lead then to ineffective decision making. At the same time, electrification, or again, I'm going to actually use the broader term of energy systems integration here, requires harmonization across systems. So again, if we come back to our electric vehicle example, this is clearly a question that sits between the power and transport systems. We could also think about hydrogen and Andrew's panel from Monday, making a comeback partly for long-term, its capability as a long-term storage asset. And this is obviously an issue that is sitting somewhere between the power and fuel systems. We could even think about, climate change in its broadest sense, driving uncertainty in water availability for hydro-based power systems like BC's, really, highlighting the link between the natural and built environment. So what we're seeing is this sort of, integration across different spatial temporal resolutions, which I'm going to show along the x-axis here, at the same time as integrating across infrastructure systems, which I'm going to plot against the y-axis here. And what we're trying to do in the CESIT team is really fill in this space with a suite of modeling tools that are intended really to interconnect with one another. So what we're striving for is a platform, which I don't want you to think of as individual models, but rather as a holistic platform, which we can then leverage to address sort of any number of questions within the energy system transition and decarbonization space, rather than as a specific model designed to look at a specific research question. So in today's panel, we're going to talk about two examples or ways in which we're sort of putting this concept to work by integrating different combinations of these models to really get at distinct research questions. So the first one we'll look at is linking across the building, transport, and power systems at the city scale to look at the City of Regina's 100% renewable energy target. And then secondly, we'll look at the gas model and the power system model to explore the potential of hydrogen injection into BC's gas system. But to make this whole platform work, it isn't just the models themselves, which I'm showing under pillar B here. We also need, vast quantities of data to support these models, which have to be, properly organized, version controlled, transparent, all that kind of good stuff, as well as a means to communicate the results of these models, which, the results sort of scale with the complexity of the model in some ways. And so visualizing and articulating the results of these models also becomes a key pillar in itself. So this is sort of where these two sort of supporting pillars on the front and back end, pillar A, what we're calling the coders database, and pillar C on the right hand side, the visualizations, really supporting the models that are sitting in the middle in pillar B there. And then finally, we need some way of actually gluing this whole framework together. Basically, this is an exercise in gluing various pieces of software together. And that's really where the Spine platform comes in. So in today's panel, we're going to start off with a presentation from Jake talking about Spine and how he's using Spine to really pull all of these different pieces together to sort of glue all of these three pillars together. We'll then launch into a presentation from Dustin and Tristan talking about the coders database. And then we'll launch into our first example of integrating these models together with a presentation from Maddie, Robert, and Lauren, looking at integrating buildings, transport, and power systems at the municipal scale. And then we'll have a presentation from Tamara, looking at sort of our second example of integrated energy systems or integrated models looking specifically at the gas system and the power system. And then finally, we're going to wrap up with a presentation from Mo and Mohammad, who have been developing a visualization suite, sort of spanning across all of these models. So with that, Jake, I'm going to pass it over to you to kick off our first presentation, and I will stop sharing. You're on mute, Jake.
Thanks, Madeleine, so much for that introduction and for the great presentation to start us off. I'm just going to get things ready real quick. Okay, can everybody see that just fine? All right.
We can, yeah.
Awesome. Good morning, ladies and gentlemen. It's a real pleasure to be with you all today. My presentation will be about the SPINE platform and the 3 pillars that support an effective dialogue around energy system transitions, which include an energy system database, a suite of modeling software, and a suite of visualization software. More specifically, I will further introduce the 3 pillars and discuss how we will apply the SPINE platform to integrate them into a complete software package for energy systems analysis. But first, I'm going to start off with a multi-select poll question that's supported by Slido. Can you all navigate to the link provided here on the slide and enter the code provided? To go through the question is, what are the biggest challenges in developing open source energy systems modeling software? Some of our options are packaging and distributing to collaborating researchers, version control, connecting large numbers of software packages, conflicting package dependencies, and also illustrating the underlying model structures and overall process flow to stakeholders. There's also sort of an option for other, if you want to put those into the chat today. Yep, you can also scan the QR code seen on the screen, and that should take you right to this poll as well. Thank you, Lauren, for pointing that out. Okay. Okay. All right, give a few more seconds here. They're coming in now. Absolutely, you know, and we'll kind of proceed from here. I mean, in reality, the fact is that all these are major challenges to consider when developing any open source software. But we as energy systems modelers understand that this one right here is actually quite important, illustrating the underlying model structures and overall process flow to stakeholders. I mean, we must communicate these to the decision makers so that we can get the policy that we see will lead us to a decarbonized society. So let's kind of move on from here. You know, the main gaps that our group has identified for open source software for energy systems analysis is, you know, one, packaging software in an easy to use design environment, allowing people to manipulate the code that we develop, you know, more easily and allowing them to connect it to other pieces of the software that they develop themselves. The second gap we see is a lack of a platform for communicating the underlying structure of modeling frameworks. There's a real gap from getting from the code all the way into essentially people's brains and for them to understand exactly what we're simulating and what the implications are. And the last but not least is, you know, there's a lack of applications for evaluating across several energy system modeling frameworks at once. Really, we're lacking this integration feature. And we believe the SPINE platform can help us to fill these gaps. But first, let me introduce you to SPINE and what it means as a platform. So what is SPINE? Well, SPINE is an energy modeling toolbox that allows for the open, practical, flexible, and realistic planning of future energy grids. The toolbox is modular and adaptable, can be applied to large-scale problems, and allows for detailed modeling of complex features. The SPINE platform can be applied for a broad set of problems, especially with the energy system space, which improves reusability of data and tools, which we know is very important for efficiency in this space. SPINE is designed to facilitate and expedite flexible model creation and development, and provides an interface to multiple modeling languages, including Python, Julia, and GAMS, which is the general algebraic modeling system. Now, the next question is, why should we use SPINE? Well, one feature that Madeleine, maybe she didn't point out in her initial presentation, but we know this is big for this project. is one feature is being a strong need for new modeling platforms is the need for them to be computationally practical and policy relevant. And really speaking to that point, let's talk about some of the modeling languages that there's an interface to Spine. Well, most of our models are actually written in Python. So this is a compatibility feature, which is, very advantageous for us in using this as an integration software platform. Spine also has the ability to connect software written in different languages into a process workflow. It's relatively easy to package an entire project of connected software, which becomes quite important when passing to collaborators. And last but not least, Spine has an aesthetic design interface that allows for easy communication of model structure and system design. And there's a bit of a figure here to show you kind of what that looks like, a very simple process flow. Moving on. What I want to show you now is an abstraction of our proposed integration. This shows a clean connection of the three major software components fitting very neatly inside of the Spine platform. Input data is pulled from the database of energy system information. It is then processed by a chosen modeling package or an entourage or suite of modeling packages, depending on what your analysis calls for. And finally, output data from modeling packages post-processed by the visualization toolkit to create interactive plots for analysis. Now let's take a minute and let's not forget about the decision makers and where they fit into this diagram, interacting with the Spine platform, but also interactively with the visualization suite as well, with the dynamic plots that come from that software. So what I want to do now is talk a little bit more about the three pillars, and we should chat a little bit more about the database and what this database is. We'll talk more about it later, but for now, just consider this. Essentially, this is a database of Canadian energy system information, mostly from the electric utility sector as it currently stands. The database was developed in MySQL, and an API has been created to pull the contained data, making it easier for those who want to use that contained data. The main goal of this database is to create a standard for input data for energy systems models. There is also the goal of developing a community to build this into a living database and to expand on the information that is currently stored. I mean, moving beyond electric utility sector and maybe into the agricultural and water sectors, which also have huge demands for electricity and energy more broadly. The next pillar is the portfolio of models that we have. We have silver, copper, building, and an EV transport model. Again, silver is our asset dispatch and production cost modeling framework. That works very well with the next framework as well, which is copper, which is a capacity expansion model. We very much need the first and second model I talked about here for efficient planning of electric utility systems. The third and fourth are the building energy demand simulation model and the EV transport model. Of course, that becomes very important as EV adoption kind of spurs over the next decade or so. Some of these models have coarse temporal resolutions, such as copper, which is on the years or decadal level. Others can have finer resolutions, such as silver, building, and the transport model. This will become important later in the presentation and in our research overall. I'm showing you now is the visualization suite, which is the last pillar. This illustrates output data from the modeling suite that we have. The visualization toolkit that CSIT has built develops two standards for input data formatting, one format for fine temporal resolution and another format for coarse temporal resolution. The toolkit uses the panel application to host interactive plots produced by the Bouquet and Matplotlib visualization libraries. Our goal is to help facilitate the creation of dashboards to convey model findings, totally changing the user experience of interacting with these energy system model outputs. So what I want to do now is I want to revisit the Spine integration feature or figure from earlier so we can set the record straight on how the Spine toolbox will actually integrate the three pillars. The Spine platform is the backbone of the entire integration, hence the name Spine. As each pillar of software interacts directly with Spine, it is only indirectly connected to the other pillars. Spine calls the database using the API, then provides the resulting query as input data into a modeling package, then takes the output from the modeling package and sends to the visualization toolkit for the creation of an interactive plot to be used by the decision makers. It is important to highlight that Spine is the primary gateway into the coders database for the CSIT team in the short term. And this is because of licensing issues that we have for now. We're in the process of licensing. So in the short term, we have to be a little bit more safe about how we package this for our collaborators. So having Spine makes it a very easy way to pass this to our collaborators because you can fit this very nicely within a project. So what's the big picture here? What does this enable us to do? And what's the real advantage of the package? Well, one, it's packaging up our software, as I've mentioned several times, and sending to our collaborators. Developing a solution for bundling a suite of modeling scenarios that can be easily analyzed by policymakers, making this a lot easier for them and lowering the barrier to entry to sort of sift through all these analyses at once. And last but not least, a simple interface that is suitable for stakeholder engagement, which will allow us a better means to modeling to generate alternatives, provide a new medium for participatory modeling, and will provide a form of communicating model structure that is appeasing to those unfamiliar with programming structure. And here's my last slide, is what's next? Integrating the database, modeling suite, and visualization suite. I mean, we've very easily integrated the database and the visualization suite for now, and we are in the process of putting the modeling suite in the middle. There's not much left to do on that, but actually once we get that integration going, we'll be evaluating across multiple energy system modeling frameworks, a brand new paradigm for comparing different softwares. What we want to do is create a new standard for linking energy systems models, and what we want to do is build on top of that linkage. And last but not least, we want to develop a community to build on this new standard and mint new analysis tools for energy system modeling frameworks. Again, opening up us to a brand new horizon of communicating our findings and making it much easier for many stakeholders to view our data and our models and our structure all at once. And with that, I'm finished with my presentation. And I'm sure we're going to save these questions for the end. And I believe I can go ahead and pass this off to Tristan and Dustin, who are getting ready to give you a presentation on the database side of things. Tristan and Dustin, I think you should be good to go.
Thank you, Jake. Hi, I'm Dustin Aldana, and I'm with my partner, Tristan Cusi, and we're two software engineering undergrads at UVic. And over the last 4 months, we've had the opportunity of working on this CODERS project, the Canadian open source database for electricity research and systems modeling. We are software students, so forgive us if we do, our technical lingo is not up to par. We'd first like to speak on the importance of open data. Firstly, timeliness. Data collection is not a quick and easy task, and the data currently in the database was compiled over the course of almost 2 years. So in a landscape that is constantly changing, the bulk of a project should not be spent obtaining this data. Instead, we want to accelerate this process so that more time can be applied to the application of that data. Next is transparency. Oftentimes, energy system models make use of thousands of data points, which can be difficult to communicate. With the development of an openly shared and then monitored database, we were able to take an important step into the injection of more transparency into the modeling workflow. As Jake spoke about inclusiveness, decision-making in the decision-making process, there's many different people that it has to go through in order to make an impact. By having this open source database, we hope to make the inputs to these models more accessible to a broader range of stakeholders and increase the communication between these decision makers. Lastly, we'd like to aspire to lay the foundation for which the National Electricity Database can be built upon. A database that researchers across Canada can collaborate to continuously grow and add to this database for years to come. And we want it to be a database that provides reliable and consistent data for the Canadian energy system and sets a standard for input data for energy system modeling, resulting in a more reliable and consistent conclusions. I'll pass it off to Tristan, who's going to speak on the more technical side of the database.
Awesome. Thanks, Dustin. Really appreciate it. I'm really excited to be here, and I want to talk a little bit about the structure of coders and some of the components within. So to start, we've got two main components to deal with, both the database as well as the API. The database is comprised of entities and relationships. An example of an entity would be the generator, which powers a substation. And here you can kind of see how the entities fit together in these kind of relationships. The other main component is the API, and the API acts as a sort of a middleman between users and the database. When a user wants to make a request to the database, they access it through an API endpoint. Endpoints are just a call for a resource, such as a list of all the generators in the database. Endpoints can be accessed through an HTTP request, which look a little bit like the example in the bottom right corner there. And this is normally done through code inside of Python script or something similar. An example of that will be shown in the demonstration later on. Next, I'd love to talk a little bit about the practical applications of coders. So the first is integration into the energy systems modeling across Canada. Coders can be used for both provincial as well as national modeling, since the data set has resolution for either. Planning is another application. We hope that organizations will use the data for planning of future projects. Planning land usage could be an example of this, since geodata is stored within coders. Another application that is made possible with the API is the creation of a web GUI, a web interface that will make the data easier to visualize and more interactive for a user. This will also give easier access to the data and will make it hopefully available to a broader range of users. Lastly, dynamic database. The current coders database is mostly static. The data is only updated when a data set has been vetted and prepared for the database, which takes a little bit of time. However, the foundation for a dynamic database is in place. Utility companies release demand data hourly and even in 5-minute increments. So the potential to automatically connect that data into the database is definitely there. Next, I'd like to cover a question or a response to a question, and that is, how can you contribute to the coders database? The main way that you can contribute is with your data. If you have a data set, we could be able to take it, validate it through a process, and then combine it with coders to try and build it up and expand the data set that is within. Also, once coders goes public, having users interact with the software and use it for their own projects would, and giving us feedback on it, would greatly help us in bettering the project and making it more user-friendly. I'll pass it off now to Dustin for interactive component.
Thank you. We have another poll. It's very similar to Jake's. You go to slido.com or you scan the QR code. We'd like to get your feedback on what you'd like to see come from the coders database. From the API, we're able to do a lot of things, like build a website, maybe release some video tutorials, or have a forum for like discussion on the database. And if you have any other suggestions, just put it in the Zoom chat. I'll give you 30 seconds to a minute, and we'll move on.
Looks like we're getting a strong result on the websites and GUI, which we as well feel really strongly and passionate about creating something like that, because we understand the back end of the software and we have created a pretty good system. However, making it more usable and user-friendly is definitely an end goal and a way to reach out to more people.
I see in the chat clear licensing with open licenses. That is something that we're currently working on too. So that's definitely in the future. And then mostly the most up-to-date data using reliable sources. Yeah, we have all the data in the database is referenced in a master reference list. And it's easy to find where each piece of data came from. I guess we'll move on now to our demo. This demo shows the API being integrated in Spine and connected to the visualization platform. Can everybody see that okay?
Hi there. I'm getting ready to take you through a demonstration of the Spine platform. Today, I'm going to show you a Spine project that connects the Coders database with a visualization toolkit. Specifically, we are going to query generator latitude and longitude data for the province of BC from the Coders database and map it using the visualization toolkit. So let's go ahead and get started. First of all, you are looking at the design view of the Spine toolbox. There are 3 items currently in the design view, and they are all connected into a process workflow. The first item is a data connection item. This item references user-specified files to be used as input for scripts in the workflow. In this case, it is referencing a text file that contains the user inputs necessary to define the database query. When we check that out, we are defining the province as BC, and we do want to show all generators, including VRE and non-VRE generators. The second item is a tool item. This item represents a script to be run in the workflow. In this case, it is a Python script that queries the database using an API developed by the Seatle team. Specifically, this script will query data on all generators in the province of BC.
Hey everyone, this is Tristan. I've been working with Seatle to help develop the Coders database and API, and today we're going to show a short demonstration on making a call to the API and formatting some of the data. So to start with, we're going to open up this script over here that I put together, and it's going to go in 3 easy steps. We're going to start with the call to the API. This is done through a URI, which you could even throw inside of your browser, but because we want to format the results, we're going to do it inside of Python. So we're going to send out the request through the requests function and store the results inside of the BC generators variable. Next up, we're going to create a CSV file for putting the output data inside of. And then we're actually going to parse through the results of the BC generators and filter them based on their latitude and longitude data. Once we have a collection of all of the generators that fit that description, we're going to put it inside of the CSV file and save it to there. So here we are, we're going to test out the script. And as we can see, it worked, and it tells us to open up the file outputs.csv, which will be inside of the same folder. So if we open it up, we can see here that we have the 5 generators that fit the description within the lat and long data, and it's stored inside of the CSV file. Thanks for watching, and I hope you learned a little bit. Bye.
The third item is also a tool item. It is a Python script that uses the visualization toolkit to illustrate data taken from the database. In this case, the script will take the query generator data, extract latitude and longitude data, and plot all generators in the province of BC on a map. Let's go ahead and execute that now. After executing this workflow, we can see an interactive figure containing a map of all the generators in BC, and this map shows up in the local web browser. The map you see here was generated using Bouquet, which is a Python library for creating interactive visualizations. This interactive figure has the following features: the pan option, which allows you to move the map around; the lasso select option, which allows you to select these generators; the wheel scroll option, which allows you to zoom in and out of the map; the reset option, which resets everything in the figure; the hover option, which this tool allows you to hover over all the generation assets, and you can see the characteristics of each generation item, giving you an asset ID, a project name, a location, an owner, a type, and an installed capacity; and the crosshair tool, which allows you to pinpoint the generators using the cursor on the map. I hope you have all enjoyed this demonstration today. I would like to take a moment and recognize Joel Grieco for developing the visualization software shown here. Joel is an undergraduate civil engineering student with a focus in energy systems analysis. Congratulations to him for developing a very useful package of visualization software that the CSIT team will be using for the foreseeable future. Thanks again, Joel.
All right, that's the demo. Thank you for listening. I believe we're sending it over to Maddie, Robert, and Lauren.
Thanks. So I'm Lauren, and I'm going to share my screen, and then myself and my teammates, Maddie and Robert, are going to present on our work regarding the city of Regina and how we link together 3 different models in that city, kind of as an example of what a combined model framework would look like. So you should be able to see my screen now. And yeah, so whoops. As I said, I'm Lauren, and along with my teammates, Robert and Maddie, we have developed an integrated model platform that we applied to a case study in Regina. And I'm going to start off with a Slido question, which is, if you wanted to reduce your carbon footprint, which of the following actions would you seriously consider? Would you purchase an electric vehicle? Would you retrofit your home to reduce heating costs in the winter? Would you install solar panels on your roof? Or is there something else that you would do? And if you have another answer, please feel free to specify in the Zoom chat. In order to access the Slido, you can scan the QR code seen on the screen, or you can go to slido.com and enter this number. I'm going to give you guys a little bit of time to see if some people will respond. We only have 2 responses so far, now 3. Still not too many responses, but it's looking like a lot of you guys are considering purchasing an electric vehicle, which is great. And while you guys are thinking about which of these things you'd like to do, actually, let me check out the chat. So we have some good suggestions in the chat along with this, including voting for politicians who will enact regulations, stop eating beef, using better, oh, that's from a different one. So yeah, thanks everyone for your responses. You can continue to respond if you'd like. Another one is purchasing local products. But one thing that actually, so there's a bunch of different options on this slide, but actually in our study of Regina, we actually looked at what would happen if you did a bunch of different options at once across different sectors, including not only purchasing an electric vehicle, but also making your home more efficient, installing a different heating system that could be more efficient and could use electricity instead of gas, and also installing rooftop solar. All these different things combined would clearly have a bigger impact than just one of them, which brings us to our presentation. So in this talk, we're going to talk briefly first about our motivation for why we chose Regina as a case study, and also talk a little bit about why we want to create an integrated model that looks at different sectors of Regina instead of just one sector or another. After that, we're going to discuss our integrated model framework with regards to both the individual models that were used and also how they are all linked together to create one kind of mega model, so to speak. And then finally, we're going to touch briefly on our results about the Regina case study. And now I'm going to give the presentation to Robert, who's going to talk about why we chose Regina.
Sure, thanks, Lauren. So, yeah, why Regina? Well, in 2018, City of Regina, the city council there committed to becoming a renewable city by 2050. And what this entails is that by 2050, 100% of Regina's energy use would be coming from renewable sources. So our research group partnered with the David Suzuki Foundation as part of the Clean Power Pathways project to focus on Regina as a case study and investigate how our integrated modeling approach can be used to help determine pathways for a city of Regina to meet its target. So a bit of background on the energy and electricity in Regina. It's currently powered by one of the most carbon intensive grids in Canada. As you can see in this figure, this is Saskatchewan's generation mix, I believe. It's mostly dominated by fossil fuels with some amount of renewable energy on the system. But overall, there's a lot of potential for more renewables to come online. Now, on the other hand, Regina is actually located in some of the best regions in Canada in terms of solar and wind potential. As you can see in these maps, Regina is that low black star you see. And on the left, this map shows solar potential. And you can see Regina is in a hotspot in Canada. And in terms of wind, it's located in a sort of above average location for wind resources. Next slide, please. So what this...
Sorry, I don't know what the heck. Sorry about that. Let me go back to the slide we were on, which is this one. Whoa, okay. Sorry, everyone. I'm going to stop sharing for a second and change something on this presentation. We're having a little bit of a technical difficulty, but it'll be right back. If you just give me a second.
PowerPoint, am I right?
Yes. All these problems in the Zoom era. Okay, great. Fix the issue. You just give me a second. I will share my screen again.
You try talking really fast to match the slides.
Yeah, I think that's what you should have done. I don't think I should have fixed the issue. I think we should have seen how fast Robert could talk.
Right, so we were talking about Regina and our modeling work. So we just saw that Regina has a lot of potential to decarbonize its energy supply, particularly on the electricity side. It has a lot of room to add more renewables to the system, and it has a potential to do so. And if this were to happen simultaneously with electrifying the demand side, we've talked about electric vehicles and electric building, heating, and cooling technologies. So if we were to integrate those technologies with that renewable energy, this sort of is a pathway to decarbonize Regina through electrification and increase its use of renewable energy. So this is sort of the modeling approach we've taken for Regina. And one of the challenges of renewable energy, which is no surprise, is it's not really a flexible resource. It can't really ramp up and down to meet the demand. This poses a lot of challenges for the grid. And we try to address this in our model by adding flexibility on the supply and the demand side. So on the supply side, we model energy storage. And on the demand side, we model demand response, which essentially refers to consumers changing their consumption patterns to better match generation characteristics. Next slide, please. Right, so this is an overview of how we've applied our integrated modeling approach to Regina. And this is also a model that can be applied to cities across Canada or any cities in general. So you can see we've taken three sectoral models, the transportation sector, the building sector, and the electricity system sector. And on the transportation side, we're interested in vehicle electrification. On the building side, we're interested in building heating and cooling, which are large uses of energy, and electrifying those end uses. And the electricity system model essentially optimizes based on the outputs of those models to get a least cost operation of the electricity system. So one thing that we'd like to highlight is that these are operational models, and the reason they're sort of individual is because each of them are quite detailed. They're capable of simulating every hour throughout a year, and this high temporal resolution gives us the ability to accurately model renewable energy, which fluctuates at finer resolutions than an hour, as well as implementing demand response and storage at the level of renewable energy fluctuations. So a quick walkthrough of how our model works. We define a scenario involving electric vehicle adoption and electric building, heating and cooling technology adoption. And those two models predict load curves based on the technology adoption, which are then fed into the electricity system model, which predicts, among other things, renewable energy curtailment. We use curtailment as an indicator as to how efficiently the system is being operated. The lower curtailment, the better the system is being operated. So if we find that the curtailment is too high, our first step in stage B is to implement demand response strategies within the transportation model and the building model to try and adjust demand as much as possible. And if we find that curtailment is still too high after that, we add storage technologies to the system. So I'll pass on to Maddie now, who's going to talk a bit about the individual models as well as some model results.
Thanks, Robert. So looking first at the transportation model, going from left to right across the screen. So we start by implementing the transportation infrastructure of the local city, in this case, Regina, which we can then use to find travel times between destinations. Then by implementing or by inputting population characteristics, as well as historical trips from travel survey data, it can run through the TASHA model, which is the transportation model used, and then can output a travel schedule. Also considering electric vehicle charging parameters, and putting that as well as the travel schedules into a charging model, we can find the total transportation sector electricity demand. The way demand response is implemented in the transportation model is that the electric vehicle charging parameters are changed so that there is more charging during times of VRE curtailment, resulting in more renewable energy being used. The building model, on the other hand, is an archetype-based model, meaning that several archetypes are built out to represent the most common building types within the city. So the archetypes are defined based on the city data. The typical building envelope and HVAC equipment is considered for each archetype. Then along with historical weather and temperature set points, that is run through Energy Plus, and then an individual building electricity demand for each archetype is defined. Along with the appliance demand and being aggregated across the number of archetypes across the whole city, we can then find the total building sector electricity demand. The way demand response is implemented for buildings is that temperature set points are changed to utilize more energy during periods of curtailment and then use less energy during periods of no curtailment, so as to use more renewables overall. And then finally, we have the electricity system model. So we start with the inputs from the transportation and the building model, as well as look at other urban inputs such as streetlight load or traffic lights, stuff like that, to get the total electricity demand for the whole city. Then along with electricity system infrastructure and historical weather data is compiled into a user-defined scenario, which is then run through Silver to produce a generation schedule. From that generation schedule, the total system costs, the greenhouse gas emissions, as well as curtailment is determined. And then curtailment, as discussed in the previous two slides, is implemented in the transportation and building models. So just to take a quick look at the type of results we can get from this integrated modeling system, this is a scenario where we have implemented a lot of renewables onto Regina's grid. I think it's a 200 megawatt wind farm, as well as much rooftop solar as we can put on the roofs. So if we look at stage A, which if you recall from Robert's slide, is just the electrification and the implementation of the renewables. And you can see with the yellow bar that we are almost at a 50% curtailment rate. And the renewable share, the amount of renewables being used by the system is only about 65% of the total electricity generation. Since we have such high curtailment, we know that we can severely reduce this or severely increase this renewable share. So then looking at stage B is after demand response. We can see that the curtailment level goes a bit down, so we're able to utilize a little bit more renewables from that, but the renewable share is still only around 65, and the Regina's target is 100%. So then we go to stage C, where we implement a very large amount of storage, and we can get the curtailment all the way down to just over 10% and the renewable share to almost, I think it's 99.9%, which we consider a success. We can see that the system is a little overbuilt though, since there is curtailment. This would then be iterated through by changing more parameters about the amount of renewables on the system, as well as potentially electric vehicle charging and building set point parameters. So that's just an example of the type of results we can get through the stages of our integrated model. And I think that's all we have for you guys right now. Again, we'll save questions till the end of the panel, but thank you all for listening.
Yeah, thanks guys. And I think Tamara will be talking next about an integrated model that she's building.
Oh, sorry, I'm still muted. So can everybody see the slides over here?
It's all good.
Okay, perfect. Yes, so I am focusing on the integration of the power and the gas system here in BC on a provincial level. And as a start, I just want to present a little motivation why we're interested in the gas power integration. So especially in BC, where we have large amounts of renewable energy generation. But within the next years, the energy demand overall is expected to increase, which also means the demand in the fossil fuel sector is expected to increase as well. And because we have such a high share of variable renewables here in BC, there's only so much we can do to meet the carbon emission targets when we're focusing on the power sector. So decarbonizing the fossil fuel sector is actually something where there's a lot of potential to reach those carbon emission targets. And we also have some issues. If we would electrify like all of the fossil fuel demand in the future, we would actually, or the demand would actually exceed the available capacity here in BC. And so integrating the power and the gas system is really a strategy to kind of explore different opportunities about improving system flexibility, but also system security and efficiency, and kind of highlight the interactions and interdependencies of the two systems. But when we're talking especially about reducing carbon emissions, it's not just electricity and natural gas that's important within an integrated gas power system, but also hydrogen. So understanding that green hydrogen, which we would produce from excess renewable energy by electrolysis, would serve as a drop-in for replacement in the natural gas grid, but also as a seasonal energy storage in the electricity sector. Using the existing infrastructure we have already holds a lot of potential. The only downfall is that the cost of producing green hydrogen is still so much higher than like blue hydrogen produced from natural gas. But when it comes to integrated power and gas systems modeling, there's really three issues we're finding in the modeling world, which is first, a lack of individual gas system models. So while there's a lot of power system models out there we can choose from, there isn't much available for gas system models. And all the integrated energy systems that are out there have a very low spatial and temporal resolution. So they look on like Europe as a whole continent or a single countries, but there's nothing really on a state level. And most of them are kind of looking at yearly temporal resolutions. And while the benefit of hydrogen within natural gas networks, but also for seasonal hydrogen storage in power systems has been evaluated, the overall benefit in an integrated setting needs a little more attention. And so really for the model integration work, we're focusing here on silver, like the electricity dispatch model, which also contains like day ahead unit commitment and optimal power flow, and just to kind of represent BC's power grid as realistic as possible. And it also includes storage, but it's limited to a daily and weekly duration right now. So we want to extend this to make seasonal hydrogen storage work. And as a gas network model, as I said, there isn't really much available, but we did find some open source gas network models that were developed by the Los Alamos lab in the US. So we're trying to use that gas models, which is based on a Julia programming language. So that might be something we could also integrate in Spine in the future. And we want to connect those two. Before I'm going into how we're going to link those two apps, I just want to kind of also target data inputs and visualizations and why they're so important, as we said before. So because we want to obtain data from power companies, but also gas companies, or from on a provincial scale, that data is not necessarily in the same format or whatever, which makes the integration and therefore the analysis of the results even harder. So only with consistent data across the models, we're actually able to produce credible results. And the visualizations platform, which is going to be the next presentation, they just allow for better analysis of the modeling results. There's some interactive visualizations on that platform where you can zoom in and you can kind of adjust the time frame you want to look at. And so it's just better informed decision making, and also makes it easier to formulate policies. So now when we're looking at model linkage, we really have three options, which is soft linking the models. So we have a manual information exchange, and then hard link would be an automated information exchange, and integrated models are really integrated so they run as one model. So the thing is, because we're using Silver and it already exists as like a standalone model, the soft linking approach is actually beneficial for us. But at the same time, the individual research questions we want to evaluate drives the need to also define what are the input and output parameters we want to use to actually connect the electricity and the gas model. So for instance, when we look into resilience of the system, we could have natural gas prices and natural gas demand as input and output parameters between the models. So the electricity model would give us a natural gas demand, for example, in a time frame where it's like really cold, in order to meet the electricity demand. And then the gas model would give us a natural gas price, which would then again affect dispatch and investment decisions within Silver. And then on the other hand, if we would be interested in system flexibility, for example, we could look into what are the storage levels within both models, like the line pack flexibility in the gas model, but the electricity storage within the Silver model. And so I have here one question: what you would think would be another sector that would benefit, or what we would benefit from when we integrate the power and the gas system. So you can kind of rank on the Slido again what you think would be the most important one. We have the transportation, heating, building, industry sector, or other sectors. So I'm just going to wait here a minute to see what everybody suggests. Seems like we're kind of jumping back and forth a little bit. I'm gonna wait a little longer. So when we're talking about using hydrogen within an integrated energy system and injecting it into natural gas grid, it automatically affects the building sector, the transportation sector, but also the industry sector. But one, what I would think would be most beneficial in but more as a long-term strategy would be integrating the transportation sector, where we would be able to use hydrogen directly as a transportation fuel. But for now, I think the easiest way to kind of see what hydrogen can do to an integrated energy system is integrating it in the gas grid, and also making sure that we have seasonal energy storage within silver. And that was it for my presentation. And I think I'm gonna stop sharing here, and Mohammad and Mo are up next.
Okay, good morning, everybody. Do you hear me clearly?
Everything should be good to go.
Okay, thank you. Okay, good morning, everybody. So I will be presenting on the third pillar, along with my colleague, Mohammad Miri, on the visualization platform from the energy models from the CICIT group. Specifically, I will be discussing about the background of the visualization dashboard, the overall objectives achieved during this exercise, and the methodology used to develop the platform. And at the end, we will be showing you a video tutorial of how the overall platform works. Next slide, please. Okay. So based on the Canada's commitment to the Paris Agreement, numerous studies developed modeling tools to investigate the policies and to bring insights for the energy system transition towards a decarbonized future. So these modeling exercises produce diverse outputs which need visualizations or dashboards to bring better understanding for the non-experts, such as policy analysts, stakeholders, and other communities. So visualization in terms of plots and charts are effective tools to communicate model results in an accessible way, which can then foster meaningful insights and effective decision-making. So the visualization options vary from model-specific or generic plot scripts, proprietary visualization formats, and sometimes visualization dashboards. So some of the background on the visualization dashboard. So the most common ones, or the most famous ones, is the EASYS, International Institute of Applied Systems Analysis Scenario Explorer, which allows to integrate different integrated system model results onto a visualization dashboard. And the other one, which is quite famous in the is the NREL's Magma and Kaleidoscope. But these visualization platform, or the visualization platforms in general, have some limitations. So specifically the Scenario Explorer, which is restricted to the IAMs, and some of the visualization platforms are model specific, and some of them are sectoral, and high resolution models are not still communicated to the stakeholders efficiently, or the very region specific models are not really integrated into these visualization dashboards. So the objectives of the work we carried out in the past 4 months was to basically, based on the limitation and studying the needs from the modeling and policymaking community, we looked at the objectives by developing an integrated platform that include 5 different types of models. So which is already mentioned by Jake and others. So integrated assessment model, capacity expansion model, electricity operation model, transportation model, and building energy simulation models. So this research specifically develops a process flow to convert the results of the model into a standard data format. So we chose 2 different standard data formats where the modeling results should be reported in that particular format, and then this develops a set of plotting functions that use the standardized results to create figures with interactive widgets to allow for quick multi-platform comparisons. And it also accommodates a standardized but flexible format for reporting different model outputs. And at the end, an important thing that it makes sure that all of the code is following the open accessible and transparent manner. Moving towards the methodological workflow of building a visualization dashboard, or if somebody wants to integrate their model results onto the visualization dashboard. So we assume an energy model X here, and then we identify or develop a standard data format first, because this is very important. So we develop a standard data format in order to be able to be reported by the modeling community to that particular data format, and then we post-process the output based on the requirements. So such as the aggregation of different variables or aggregation of different variables onto specific regions, and then these outputs are characterized based on different variable types and scenarios and regions. And then this is integrated to the visualization dashboard through different plotting functions in Python. So in general, our whole platform is actually developed in Python programming language, because all of the SysID models are mostly developed in the Python language. So, and also that Python is widely used amongst the various research communities in the energy system modeling. And we use this panel library in Python to integrate our visualization tools on the dashboard. So basically a little bit about the panel. So panel is an open source Python library that allows user to create custom interactive web apps and dashboards by connecting widgets such as the drop-down menus, sliders, and buttons to the plots. And these plots are, for some models, these plots are basically dynamic and interactive. And for some model, we are doing the efforts to make the plots really interactive for the users. The decision to use panel was basically based on what it provides. So basically, the panel package for Python provides a stable platform where we can host different apps for the models. And also panel hosts its own tutorial showcasing common operations. And also the project is openly accessible through the following GitLab repository. And it also uses all of the open source libraries, and we actually invite contributors and different energy modelers to contribute to the whole project, or maybe submit their models to be able to integrate into the visualization platform. And in order to read the more detail about the project, the report is publicly available at the Energy Modeling Initiative website, where there is all of the details and the user manuals for the project. In future, we also plan to upload this visualization platform to a live website, and also host a documentation which allows the users to be able to well integrate for their own models. Now we will be showing you a video tour of the platform. So I would like to give a shout out to Preet, who's an undergrad student, and he worked with us during the past 4 months and developed most of the software related work of the platform. So, Jay, over to you.
Hello, my name is Preet, and today I will be guiding you through the visualization platform created by the SysID team at the University of Victoria. Here's the first component of the platform that shows the interactive results from the Message IX Canada Integrated Assessment Model. The drop-down box allows for the selection of various variables such as primary energy, costs, emissions reported from the model. More drop-down boxes can be added given further availability of modeling results, such as navigating between scenarios, filtering out regional results, as well as scenario comparison plots. The second component of the platform shows interactive results from the copper model. The drop-down box allows us to navigate through the modeling results of various variables, 5 different carbon tax scenarios, as well as regional results from each province in Canada, as well as a total overview of Canada itself. Here are some of the various plots you will be seeing if you decide to play around with the functions. The third component of the toolkit shows interactive results from the silver model. These interactive plots allow more user-friendly options, such as zooming into specific parts of the plot, or even being able to pan the graph around to get the exact angle that you would like. Furthermore, zooming into specific parts of the plot and visualizing the aggregated time series data, you can see that the time on the bottom here adjusts, and you can kind of filter the graph to see specific portions of time that you would like to see covered. The drop-down option to choose between different parameters of results are exactly the same as seen before. There are two different scenarios in this case. Another important feature is the legend up here. This legend is interactive. If you would wish to remove some pieces of data that you do not wish to see, simply click on its name in the legend and it will disappear. Click on them again and they will reappear. Another relevant tool in the silver model is the use of the box zoom. On this left-hand section here, there is a small magnifying glass with the label box zoom. If you click that, it will enable for you to be able to pan and cover a specific portion of time to your liking and get a zoomed in version of the data. The reason why this is so useful is the data does not get morphed. It kind of spans to fit the whole graph in front of you. If you would like to zoom in some more, you can do that as well. Simply draw another box and you will have some more data to look at, as well as updated time values at the bottom. The transport model works in a very similar way to silver. The interactive legend exists here again. The time series data exists as well. Simply zoom in. As well, there is one variable box here, designed to take different months of data. The buildings model works in the same way that silver and transport does. Once again, you may highlight and unhighlight different pieces of data depending on what you wish to see, what you don't wish to see. There is a scenario option to load different pieces of data. And in the case of this one, you may zoom as well. And that would also load the time series data and updates the legend accordingly. Thank you for following this guide on the visualization platform created by the CESA team at the University of Victoria.
Okay, so at the end of our presentation, we actually haven't decided on a name for our developed visualization platform. So we wanted to ask for your opinion about these options that we thought of, and also if you had any suggestion or a name for our visualization platform, please go ahead and put it in the chat, in the Zoom chat here. So if you want to vote, please go to Slido and go for the number shown here. And the options that we thought about here is the first series, scenario explanation and explorer repository, idea, integrated dashboard for energy transition analysis, EET explorer for energy transition, and VIDRES, visually investigating decarbonization routes for energy systems. So we'll have a little bit of time for you, please, to vote about these options, or if you have any other option names. Okay, so yeah, thank you so much. Yeah, it seems that the idea is more interesting for you. I also, I mean, myself, like this is Mohammed's idea. So yeah, thank you all. This was our presentation, and I think with that we'll go back to Jacob to wrap up the 3 pillars. Thank you so much for joining us.
I believe Madeleine will be going on.
Yep, just sharing my screen there. Can you see it?
Yes, everything's good.
Great. Okay, so just to wrap up now, we've taken you through a little bit of a whirlwind, and to be honest with you, this is actually the first time I think we've put all of this together into one presentation. So it's pretty exciting, I think, for us to see this coming together a little bit, or it's pretty exciting for me anyway. So we've sort of walked through these 3 different pillars, and to wrap up, I want to bring you back to our objective. And so we've been chatting so far mostly about that sort of first part, modeling the electrification and the different components of doing that. And now I want to move on a little bit to the second objective there, which is really supporting the actions that can lead to deep decarbonization by delivering relevant and impactful insights to decision makers. And so along these lines, I want to articulate a little bit more what the challenge associated with doing this actually is, with doing this translation, what that actually is. And through a project a few of you are involved in, the Energy Modeling Initiative, it's a project funded by NRCan, which is really around convening decision makers and modelers who are focused on decarbonizing the energy system. And over the past couple of years, the EMI has engaged in a number of regional and national workshops that are really trying to understand where the challenges lie when it comes to integrating model-based evidence into the decision-making process. And there were sort of 3 critical but lacking components that have sort of cropped up in a few of the presentations we just listened to, associated with integrating model-based evidence into the decision-making process. And this really comes down to timeliness, so the ability to deliver insights to decision makers in a way that's actually practical for them, transparency, and this comes down to collaboration, but also the trustworthiness of the models themselves, and inclusiveness. And so our hope with this platform is really that to be able to assemble the data and models, and what we're sort of thinking of is this kind of standing army repository that can be called upon whenever we need it. And a number of the questions I saw there in the chat were about, is this open access? And definitely that is the intention. We have a ways to go with the UVic legal team on making that happen, but making all of this open access and accessible to people through GUIs and also to models, and a broad range of people coming to that third point on inclusiveness, people from across campus, different perspectives, different stakeholders, and bringing them into the process sort of where they're at, whether that's in the modeling process, whether that's in the data collection process, whether that's in the question and scenario making process. So what I'm sort of hoping for longer term is to bring these 2 objectives together, the sort of modeling suite and those 3 pillars that we've been talking about, with this sort of upper level stakeholder engagement piece, and doing sort of working through a process with stakeholders that really leverages this capacity and pushes it forward into that decision-making space. So looking forward a little bit, where do we plan to go? And I think in my mind, there's sort of the two aspects here. There's the what, which is really, I think, that holistic perspective on energy systems decarbonization, which is the platform that we've been talking about, and continuing to build that platform out and extending it with collaborators. I'm hoping we've captured the imagination of a few of you on the call to get in touch and to to think about how we could collaborate with this platform and developing new links to new models, new data, and new visualizations. And then there's the how, right? How are we actually going to go about implementing some of these resources, some of the software into the decision-making process? And I think the key words here are really iterative, collaborative, and ongoing. So continuing our work on with the energy modeling initiative, I think is an important one there, convening and leveraging Canadian modeling capacity to support decision makers moving forward. So future activities, I'm hoping to, especially post-pandemic, sort of continue the series of modeling forums and grow them, really focusing on modeling teams and modeling themes. And then also, an ongoing series of forums that are perhaps more issues-based, focused on questions that modelers and decision makers have. So that wraps up the presentation portion for today. And so happy to take questions at this point. I'm going to stop sharing my slides there. I know there's been a number that have come in the chat, or if you want to just take your video off and you turn your microphone on, we can do them live as well. So any questions?
All participants should be able to unmute themselves and start their video if they'd like to do so now. Maybe we'll start with a question from the chat. This one comes from Curran Crawford. What about industrial loads for heat and cogeneration?
Do you want to be a little more specific there, Curran? Who is that? What about industrial loads? What's your question? Are we thinking about that in our modeling? Is that the question? Or is that, maybe that's the Regina, maybe Maddie and Robert, maybe that's directed at you. Not totally sure. Or maybe that's Tamara, I'm not sure.
Yeah, I think it was about the power gas modeling framework.
Okay, Tamara, do you want to take that one?
Yeah, well, I don't know, we haven't considered it yet in what we've talked about, but I know that there's cogeneration plants in Germany that just fully operated on hydrogen. I think that started last year, so that is definitely something we probably want to take into consideration in the future and kind of see what they've been doing and what kind of benefits they're getting.
I believe Theo has a question here. Can you, there you
Hello.
go.
This was a really awesome presentation, and I'm really interested in all these data models and data stuff that you have in the open APIs. I think that could be very interesting, also for the stuff that I'm working on right now. And having all these models together is really cool because you can explore certain scenarios that you would never be able to do without having all these models tied together. The one question that I had, it wasn't really talked about much in the presentations, and I'd love to hear your ideas about it, is how do we prevent small errors of each model creeping into the eventual solution that the model provides? Like if there's small errors, maybe they sort of, keep expanding and we might get something that's totally unreasonable. So yeah, maybe you can elaborate a little bit on that, maybe have some thoughts. I don't know.
Maybe Robert, Lauren, and Maddie, in your model integration, did you see any of that errors sort of propagating through?
Well, definitely with the buildings, there was some, maybe not such an error, but more like we didn't necessarily always have the data that we needed to really we didn't really have all the data that we needed. And so sometimes I would make certain assumptions just based on what I thought was likely, or for example, in the case of building archetypes, I didn't have detailed information for each building, and so I just estimated based on the census, kind of like what an average building might be like. And like definitely that is something that has a big influence on the results, but doesn't come from, like, yeah, it is like whatever assumption we make, that ends up influencing the results a lot. And so by changing those assumptions, you could potentially end up with different results, which could be like of interest.
Yeah, and just to add on to that, I mean, I think compounding errors and assumptions is going to be an issue in kind of all modeling work, but especially when we're integrating several models like this. So I think what's maybe what our models should be viewed as is more comparing scenarios between each other more so, as opposed to finding a final number that is 100% accurate. Because I mean, what's that quote? Not models aren't right, but some of them are useful. And I think that's kind of in general how we need to look at modeling work, and especially when we're doing integrated stuff like this. Like as Lauren's saying, maybe a slight assumption is going to have a big influence on the final number, but we can still compare scenarios to each other. So even if it's just like, oh, this scenario will cost 5 times more, maybe it's more like 4.8 or 5.1, but it's still kind of the ballpark range for what we're looking at, would be my thought about those kind of compounding errors. And that's just kind of, I think, how our results are going to need to be viewed until we can really hammer down all the exact data that we need.
And I guess just adding on to that, I mean, I think one of the sort of interesting and challenging things about trying to do a multidisciplinary project like this one, especially as we start to get in outside of, let's say, the classic engineering realm and more into economics, as we look at energy equilibrium models or integrated assessment models or even climate models and things like that. So much of the language that we use in our ideas around everything, I mean, even the word data, you know, means something totally different to an economist than it does to an engineer. So we're constantly having to sort of define those terms. And I think validation and error is another one where even within the engineering discipline, we have different ideas about what that means depending on the kind of models that we're running. So if you're running sort of a physics-based building system model, you know, that can be validated against a real system and that has more certainty associated with it, because we understand things like material properties or fluid dynamics better than we understand, let's say, decision making of interprovincial transmission lines going out to 2050, right? So it's sort of, there's this kind of, when we're taking this multi-model, multidisciplinary perspective, we start to cross boundaries like that I think are part of the challenge associated with the work, but it's also, I think, one of the ways in which we do have to coordinate and convene our conversation and the way that we're talking with one another and what we mean when we talk about certain things. And so yeah, so I think that sort of, I think that it's I guess, taking a step back from the question itself, I think it's a good way to sort of highlight where some of these barriers are with trying to do this kind of multidisciplinary, I mean, multi-model, but ultimately multidisciplinary work that, you know, talking about errors in a general equilibrium model with battery costs that are being extrapolated out to 2100 means something totally different than talking about errors with a building system modeler who is representing an existing building and can validate that against, you know, measured data. So it's sort of, yeah, it's not really answering your question, but I think highlighting one of the barriers, but important barriers that I do think we have to really sort of take head on.
I believe Kevin's got a question. If he'd like to go ahead and unmute himself.
Madeleine, this question is for you. Thank you for putting this together as an overarching strategy, putting all these models together and then providing that information to policymakers is really where I see energy system modeling going as a service. I'm wondering what's the goal? So I've heard from policymakers that they would like to have transparent models that they can use for evidence-based policymaking, but at the same time, they probably wouldn't want to deal with, the nitty-gritty. So sharing the models with policymakers is important. How much service do we, as modelers, provide to them as almost consultants, and how much work do we leave to them? So what does the final product that we deliver to policymakers look like as a software?
Yeah, I think I'm sort of two minds there. I really like the idea of the modeling community coming together sort of at the front end and not necessarily coming together around pieces of software. I think it's good and great that we have different models that have different formulations, that have different baked in assumptions, that have different perspectives or worldviews sort of inherently baked into them. And what I would love to see is sort of, policymakers or decision makers kind of coming up with the questions, like they know what's on the table, right? They know what they can and cannot do, what options are available to them. And like the Atlantic loop, I mean, is a big one that's being talked about right now. And there's questions around the Atlantic loop that are technical, but there's a lot of stuff around the Atlantic loop that are the personalities at the table, historical context, other things that as modelers, especially modelers sitting in BC, we're not going to capture, right? And so I think that there's some work to do on the side of decision makers and policymakers to really frame up the question. And I think a huge piece of work that is maybe lacking a little bit, even in our language, we sort of talk, and I do this too, we talk about decision makers and we talk about modelers. And I think there's actually an individual or a profession in the middle who are the translators between the two. And so, how do you take the questions from decision makers, formulate them, write them down in such a way that they can actually be inputs to models? And in my mind, a multitude of models. Like, again, if we come back to the Atlantic loop, we've got capacity expansion questions, we've got, optimal power flow questions, we've also got transport questions and building questions, and it's all sort of wrapped up into one. And then there's, the osmosis version of capacity expansion versus the message version versus the copper version, which have different formulations and are going to lead to slightly different ways in which they're handling errors or uncertainties that are going to propagate through in different ways, right? So so in my mind, it would sort of be this translation between the question being formulated, translated in such a way that it can actually be an input to models, running it through a multitude of models, and then seeing where our insights and our advice is robust or not, right? Like if all of the models are coming out saying, this is a clear pathway, or this is clearly not a pathway, that's a much more robust result for a decision maker to take home than, oh, well, on the margin, osmosis said this, but copper said something different. Okay, well, maybe that's not something that we bank our future on, so it's sort of using the multi-model approach and the multidisciplinary approach to come up with something a little bit more robust to uncertainties. And then again, I think there's a lot of work translating that back to the decision makers themselves. So coming back to Theo's point, how certain are we? Where have the model, where have errors potentially propagated through? What has our sensitivity analysis led to in terms of understanding what we're very confident about saying versus what we're kind of like, for 5 cents, build asset A instead of asset B, but do we really care about 5 cents kind of thing, So I think, yeah, I think, so where does that go? I mean, I would like to see a more iterative and ongoing approach between decision makers and policy makers, not this kind of one-off consulting thing where there's, you know, a call comes out, you know, a certain amount of money is put on the table, you know, 6 months to a year goes by, some report is written and we call it a day and we send it back. You know, I would like to see something that's a little bit more iterative and ongoing, you know, and as things change and as, you know, as we get more insights, as things are built, as new people come in and out of office, you know, that sort of continues to evolve with all of that.
That's interesting. Yeah, thanks for that. So what I'm hearing is we really need the energy system modelers to develop the models themselves, go deep into the code. We need a person in between, so kind of maybe the user of these models who can translate between the policymaker and the model developer on a continuous basis, and then the policymaker would not necessarily be involved with actual using the model, but formulating the questions and making the conclusions or drawing the conclusions from the results of those models. So those are really that's really a tiered development process. Did I understand that right?
Yeah, I mean, I think it really also comes down to the individuals, like, you know, the city councilors in Regina, for example, you know, I would say they're sort of surprised, or City of Vancouver is an even better example, like surprisingly technical. There's a lot of engineers in that office who actually, I think, probably do want to play around with sliders, and they actually do maybe want to take a look at the code, you know, and so having the option to do that is there. But then there's other, you know, policymakers, but there's just no way that they have the time, the interest, the background to be able to go in and look at the code. So I think what we want as a community of academics or as modelers is to have to put in place platforms that are flexible enough that, you know, individuals with different capacity, different time, you know, different timelines, different resources can interact according to their needs, right? Or, you know, or according to sort of what the options on the table there at the time. So I'm not sure that I would say, you know, no policymakers should ever play around with models, or all policymakers should be able to play around with models. I think it's kind of up to the and then within NRCan, for example, the team that sits within NRCan, I'm thinking, you know, in particular, the one guy who really does, like, he reads the papers. Every time we publish a paper with a new model, he is reading it. He's sitting at NRCan and he knows, he can tell you about osmosis. He can tell you about copper. He can tell you about silver. He's reading these papers, and there he is sitting at NRCan, right? And he's working within the NRCan system. So I think at some point, I think it's sort of the individuals who happen to be in various roles. So I'm not sure that I don't think I would necessarily make a generalization about that one way or the other, but rather to set up platforms and resources that can suit different needs and different people as they kind of come and go.
Can I just, hi Madeleine, just wanted to say, from coming from sort of a social science background, this multidisciplinary approach doesn't seem so new. But I think you have a problem with potentially becoming all things to all people, in that you can go so granular in some of the models. People tend to, I've seen it in research I've done, where, you know, when you can model everything, people will want to, and they'll just want to build the evidence till, you know, it's like doing so much research so you don't have to write the paper. So it's interesting, as you said, a translator between the academic side, the technical side, and the policy makers. And I think one needs to be aware that policymakers are often time constrained by politics, you know, elections, and, you know, what their constituents are. And they tend to be quite, I think this could become, one could almost do too much modeling. And, you know, show people every option, while maybe there are big issues that would be useful over a larger constituency. I mean, it's all, You know, it's wonderful to have the information, but the information can sometimes paralyze action. So I think the translation is key, because I think as I've been participating as sort of an educated, you know, or slightly informed general public member, there is a real need for analogy, example, narrative to get the information and be that explains it, but also supports all the data that can be used to hopefully change policy in an effective way.
You touch upon a really important point there. The narrative of a model is important to convey information, because these models are so complex and they spit out so much data. Making sense of that information in a way that tells an interesting story is something that ISIC is really good at teaching, I find, and writing a good paper means taking the data and creating a storyline that leads to an improvement in our society, in our economy, in terms of greenhouse gas emission reductions. And basing that on the data and telling that story is key. So that translation that you speak of is important.
Well, I think it also doesn't mean dumbing down. I think it just means finding the imagery that affects people, resonates. You know, I think one of the I think it may have been Brant Pepley on Monday said, you know, why use gold to make lead? And, you know, it was in a particular context, but it just, you know, it clicks with you and you just go, yeah, okay, I get it. And then you were so much more receptive to the other information and to the other, the details and the evidence, because you kind of get the nub of it right from the start. Any other comments?
Yeah, does anybody else want to jump into this conversation?
I think one of the things that I learned, and this is also when me and Pauline were working on the podcast together, it really does make a big difference to also kind of like curate what you're doing instead of like having everything available, because it can be overwhelming. And we all have this issue when we're dealing with so many variables, so many different things. The thing is that I think maybe the perspective from Madeleine's case is that because we lock all that thinking and all that variables into equations and into models, we can really take a step back and say, okay, let's take a look at which levers do we want to pull and how does that impact the system? So looking at that A/B testing of the different scenarios that was earlier mentioned as well. And kind of saying, okay, this is a model, we've built it, and it creates answers that we can discuss and think about. But yeah, it's really difficult when especially when you're talking about, for example, integrating transportation with energy and heating and buildings. And you know, we're also working on a different project, the PIX project, which is a project with the city of Victoria, and very similar to what you guys are doing with the Regina case, where they're really hungry for something to integrate all these different aspects and look at the problem from a holistic point of view. So yeah, it goes two ways, I guess. So there's no real answer that I have that I can offer that has a clear answer. But I do think that when you talk to some people from the city, yeah, they really do need a clear picture. Like if you go to council, in Victoria's case, when you go to council, there need to be a clear picture, clear ideas. But when you talk to the planners that are in day-to-day working on these problems, and they have read all those white papers and studies, and they'll dig into your models and say, okay, why you're not considering, you know, all these other things that for example, in a building, like parking requirements can be changed, or, the number of floors that are allowed can be changed, or there's hundreds of different things, bicycle requirements, there's hundreds of things that they think about that are not directly tied to energy in a direct way, but are tied to it in a softer way. Because if there are less parking spots, but better access to bicycle lanes, then people might consider taking the bicycle over the car, and then the personal vehicle mobility share changes, and that impacts the overall energy system in other ways that are completely unknown to anybody. There's no like empirical equation that says, okay, if you put so many bicycle lanes around a building, you're going to see people change their mobility share for that particular. And then, so there's a huge amount of unknowns, and I like to, the way I start sort of approaching it, maybe in a different way, is that I really consider it like as an organic system with some things that we may be able to change that have knock-on effects outside of the things that we actually model, that we might find in the data from other work. So we might go in, and that's more like a data approach, not like a linear model or something like that. We really look at the data and say, okay, apparently there is a correlation here, given all these different factors. And then the only way to really kind of like delve into that is have a real robust statistical analysis on such problems. And then,
I'm getting sorry, Theo, I'm getting slightly frustrated because it just seems it can become paralyzing.
Right. Yeah.
Especially,
no, totally. Yeah.
And that's the problem with the entire issue, is that people have been given in a very short time, because for years and years no one was talking about this, but now it's like a plethora of information and options, and people are always looking for the simple solution. Well, that's obviously not the case, but I think choices cause confusion sometimes for people. And I think the curation, it's a word I absolutely hate, or the curating, is important, that people get the information that they need, understand, can translate, and hopefully move into positive and actual action. Because when people see the change, then they have already bought in, and more change and more solutions can be put into effect. But I think, too much information and the ability and just knowing it's out there can stop people going, oh, it may come tomorrow that I don't agree with that, or that doesn't work for this street in my little community. So I just think it's translation, it's editing, and it's curating, and it's trying to link up the information that is the most constructive.
Yeah, and relevant. And I think, like that, the city of the Victoria, and I think it's the same thing in Regina too, and this is again coming back to this translation between modelers. We think about models like that, that sort of chart. Okay, we've got capacity expansion, we've got production costs, we've got buildings, we've got transport, we've got whatever, energy, and that's sort of how we think. That's the lens we put on it as modelers. Okay, we're modeling across these sectors, we're modeling these decision variables, we're modeling these spatial temporal scales, whatever. But that's not actually, like Steve Young at City of Victoria, like he doesn't really care what your objective function is. He doesn't care, he wants to know EV chargers, or do I subsidize EV chargers, or like I've got $10 million to subsidize something. Do I put it to EV chargers, or do I put it to building system upgrades? And in order to be able for him to delve into that question, I mean, we can put our modeling lens on that. Okay, well, you need a power system model, a transport model, and a building system model to answer that question. And you actually also need an energy economy model as well, because how are people going to respond to subsidies of different things, right? So it's like, we don't, like, anything that's part of this translation is to take it from our modeling paradigm and our disciplinary paradigm, which is, okay, well, I'm a building system modeler, and these are the physics I understand, these are the formulations that have been baked into my model, so these are the questions that I can answer, and then the options that are available to the decision maker at that time, right? And NRCan has a different set of questions, like interprovincial transmission lines. that's a difference. Like, they don't care about subsidies for heat pumps. That's not the question that they have on the table, because that's not what they have jurisdiction over, or maybe they do, but I'm thinking about the Atlantic Loop right now. What they're interested in there is capacity expansion, transmission lines, you know, carbon budgets, like a whole different set of questions, which is a whole different set of models, right? But I feel like more and more as we go down this electrification and decarbonization pathway, we get further from our discipline-based models and more into the realm of and approaching the question of the options that the decision makers have on the table, and using our models to look at those options, not using our models for what we can use our models for, which is what I mean, it's obviously way easier and convenient.
Okay, and then one thing I'd like to add, I definitely agree with you 100% there. Take whatever they can do, because they're within a legislative framework, right? They have federal, provincial, they have geographic issues, there's political issues, there's, you know, public perception and public acceptance issues. Then look at what they can do. That is already a very, very slim amount of things that they can do. But then at the end of the model, what kind of results we present? One of the things that I've found to be extremely important for this is to talk in their talk. Use the metrics that they use. So if they use walk score, somehow figure out to translate the outputs of your model into a walk score. So that's something they understand, or into a transit score, or into a, you know, we're working with the City of Victoria. They happen to use this global protocol for community emissions. It's developed in Seattle. Over 100 municipalities use it to do carbon accounting in their city. Make sure that your data is structured in a way that it's binned into those subsectors, under those subsectors, with numbers that they understand. If you say, oh, buildings are doing 20%, they don't understand that, because they understand, oh, buildings are part of several different subsectors within the GPC. You know, they're stationary, there's this and this and that. Why aren't you breaking it down to this? So it's, I would say this is my big revelation of this project right now, is go in and explicitly look at what are the planners using to talk to each other in what kind of metrics. If they're talking about transit score, copy the equation for transit score and use that. If they're talking about, you know, there are different carbon accounting systems, there are actually several tens of them. But if they're using the BC, the federal one, or are they using the provincial one, or are they using some other one, use that and then move forward on that, and make sure that whatever you're putting into those bins is actually what they think should be in those bins, which is also not always the case. Like if you read the reports word for word, you have a discussion, where does building waste go? Or how does carbon from concrete drying get accounted into one of these bins? They'll have different opinions where that should be. So it's an extremely, it's a communication problem. But then whatever happens between the levers that they pull and the frameworks that they use to talk, underneath that can be our model. And we just need to sort of like have a communication line, a data class that sucks in this piece and then spits out that piece.
Yeah, totally. And that's where I feel like we don't give enough time or energy. I mean, it doesn't really exist as a profession, right? Like where translator is not really the right word. It's like the meta discipline, like the person who can speak both languages and who can take the discipline-based models and who can understand the levers, you know, like the different policymakers have it, you know, and like that's not particularly one of our strengths, right? We can sort of try to understand, and we can sort of try to sort of inch our way closer to one another. But I would love to a new profession to evolve that is somebody who, well, primarily is really good at communicating, but who can do both of those things. Who can say, okay, well, what is it that your model spits out? What is the underlying, what kind of questions, okay, what levers do you have at your disposal, and how are you formulating your decarbonization plan? What metrics are you using? And then linking the two somehow tying the rope between them.
That's my daily headache.
Yeah, mine too. I think a lot of us, right? Like, I think a lot of us who are trying to make our models actually impactful. This is the challenge. It's like, we can talk about data being a challenge, and that's also a challenge, and computation being a challenge, and sure, that's a challenge too. But I think this is one of the big ones. I'm not really keeping up with the chat.
Just a quick end. I was just going to say, it's kind of, the analogy is like a matchmaker.
Mm-hmm.
You know, you've got two very different, and you're trying to get the best for both parties.
Mm-hmm.
I think there's one question here, right? Even as if it becomes, hey, I want to try all these options. So the following, the idea of the second presentation about databases, is one of your ideas to store somewhere typical results to also limit the need for new computing.
Yeah, and also the multi-model. I mean, this isn't something that's in there right now, but I think the multi-model comparisons as well, and then historical results as well. But a platform that really can, you know, where you could almost like flip through, you know, results for the same question from different models. So, you know, if Steve, or, you know, City of Victoria comes along, and let's say like you come up with a plan for City of Victoria. Okay, we're going to build bike lanes here. We're going to do this subsidy for heat pumps, which is going to precipitate this adoption of heat pumps, blah, blah, blah. You do this whole plan, and then you've got 20 models that go out, the building system models that model that, the transport models that do that, the capacity expansion model, the powers of and then a scenario visualization platform that could bring all of that back together, and where you could sort of flip through the visuals and tell the story of that plan or question, or you know, from that sort of multidisciplinary perspective, from that holistic, really getting at that holistic perspective. So that's certainly not something that is in the visualization platform now, but something that I think is part of the motivation of having a multi-model visualization platform, as opposed to a visualization platform that is dedicated, that is married to a specific model, is to be able to ultimately do that, and do that also, you know, I think in some ways more importantly across research groups too, right? Like not just one research group or one, I mean, that, I guess that's tied to having the multi-model, but having a number of different models and research groups where it's sort of flipping through, and then the narratives sort of come together into something a little bit more cohesive.
Yeah, I was just going to say quickly that I think it's important for the open source stuff, and to make this all publicly accessible, that all these options can be shown to the public, but not necessarily for the policymakers, the decision makers, but for other modeling groups, whereas it would be more tailored when communicating with decision makers and policymakers. Like, we definitely have that with Regina currently. You know, we rework our presentation every time depending on who's going to be there and like what they're interested in. Do they care about cost? Do they care about how they meet their target? Or do they care about the more nitty gritty, like what is the level of curtailment for each project? Whereas modelers would care about that, you know, or would care about certain variables we're changing, whereas the city most likely does not.
Well, it was a surprise, right? Like, Maddie, I was surprised in our last meeting with the City of Regina. Like, they actually did want to look at the dispatch plots, which going into that meeting would not have been my guess. But now coming out of that meeting, it's like, okay, this is where it's really ultimately at some point is just the individuals that you're speaking with, right? But coming out of that meeting, it's like those particular individuals, for whatever reason, wherever they're coming from, whatever background they have, for whatever reason, they actually do want to be looking at the hourly dispatch plots. Okay, cool, good to know. That's a visualization we can throw in there, right?
Yeah, so I think, like, as you were saying, like the knowing it all, like it's important to have it in there, but whether that's necessarily accessible for all groups of people is the question that we have to answer, in which case this translator profession would come in very helpful, you know, and
The question is, like, quickly, why do they want to look at those hourly what are the information that they're getting from it that they're now, is it just a sanity check that they're looking at?
I think at that moment in time, I think that what we're still in that particular project, I think what we're doing right now is still establishing trust. And I think that that's part of that, is they're kind of looking at this, okay, these 3 different models running, do we really, like, they've probably talked to a bunch of, well, we know they're talking to other modeling teams, So it's like, how do you garner trust? And I think there's a certain point at which looking at a dispatch plot, for example, which is way beyond the level of technical detail that you actually that they actually ultimately need at some point. But somehow I think this is totally just like off the cuff. My intuition about what was going on was there was just a little bit of trust building there. What's
because they probably have reports from consultants, and they've sit in meetings like this before.
Exactly.
And then trust is a very interesting point. I never really thought about it too much, but it's definitely something that should be on our radar as well. As part of the whole thing. And
again, that's why I think that the multi-model and multi-team thing is so important, because I actually think that's something we should be doing on our side, like on the research side of things, that we should be amongst ourselves saying, well, what does your capacity expansion model must say? What does mine say? Why are they different? Where are they the same? That we should be doing that legwork to some extent, and then coming and being pretty transparent about where we're consistent and where we're inconsistent, and what that means as far as decision making goes, right? Like, whether you take a mixed integer formulation or a linear formulation, we know that like that's robust now, or that's more robust, whether you took data from the EIA or data from whatever, some other source, like that, our results were the same. Okay, well, that's a lot more robust. That's a lot more convincing than one group somewhere coming up with some number,
It's definitely interesting to hear, though, about, because I mean, always thinking about it as a modeler, it's interesting to hear about more choices being paralyzing, because in my mind it's opens a world of opportunities, so it's good to kind of keep that perspective in the back of our mind going forward, because personally I don't contribute that to our research. I'm much more would like to see all the options laid out.
It depends on how many options, right? Like if there's 20, I think I can keep 20 in my mind, but if there's you go above 120 and all of them are like changing your model 5%. Like any lever changes, like a change in one lever with 1 point changes your model outcome of 5% or something. That could be possible. And then it becomes an exceptional, difficult problem to keep in your brain and to explain to people and to weigh your options and to figure out how do you even start something like that.
I think it's important to consider who your audience is in all of this as well. I mean, obviously the key is policymakers and other stakeholders in the community, but also to understand, how these models can be used at many different scales, right? I mean, if you could use it at one end as an educational tool, right? But another end of where you actually want to make real decisions. And if you think about like a lot of common software suites, a lot of times you typically have many different versions of them, right? You have a beginner, sort of an intermediate, and maybe an advanced type a version of a software. And as you go from beginner to advanced, you get many more options and features to include in your model, right? And so I believe that that's a good point to have some sort of, some separation there, so that if you are on an educational type conversation, maybe you should only consider 2, 3, or 4 models, right? But as you start getting more into the policymakers and they really want fit for purpose solutions, then you do give them all the options. And another thing is considering, people get quite scared with software, so to give them a version that is very beginner and very face level, right, would make it a lot easier for them and then lower that barrier to entry to actually interact with that. and giving them sort of a step or a tiered approach where they go from beginner to advanced, and eventually they start asking more questions and options than there are available to you, right? And then you can actually get more into the development side. But yeah, I just always consider that, maybe things could be sort of branched out, or, more options or less options depending on who the audience members actually are.
Yeah, and Leah actually touched on that in the chat, just saying that user interfaces would be a good way of limiting the amount of outputs, but it would totally, but while still encompassing all the model details. But that also plays into your point too, that there can be several different user interfaces depending on what the purpose of the user is, or their goal is.
Yeah, absolutely. Thank you.
So Jake, are we into the after party?
Yeah, we're into the after party session, and depending on what the other panelists or what time that they have, I mean, I'm happy to stick around for a little longer if people want to chat. We don't expect all the panelists to stay, depending on what their schedules are. But of course, people have the ability to unmute and then to start their videos if people want to be more social or want to ask more questions. It's really up to you. I mean, the last few days, we've just sort of been taking this until everyone leaves. But again, there's no pressure to do anything this way or that way. It's up to you.
Cool. So this is the opportunity to hijack the conversation and talk about your first post-COVID trip.
Not in Canada, apparently. Not yet. Not yet.
No. I'm still pretty much ignoring the chat. I see questions come in, but does your model take care of interactions with variables, parameters? I'm not sure what that means exactly, or how to answer that. Thanks, Robert. See you later. Going back.
I'm going to sign off too, but thank you everyone for coming, and thank you, Jake, for moderating.
Thank you so much for presenting.
Bye, everyone.
Bye.
Just a question about this. How long was the project with Regina? And was it just 6 months, or is this a longer ongoing project?
Yeah, it's longer, it's ongoing. We just have, we've presented, and really it's really like my keyword in that project is really iteration. Like we've gone, I don't know how many, I couldn't even go back and count how many meetings. Well, I'm sure we could, but it's just like, it's ongoing. So, and that's all. We're also working with other like NGOs and things like that. Again, on the translation side piece of things. So, but it's a lot of sort of back and forth where influencing the model development based on the feedback that we get, going back, presenting the results. And it's like, in my mind, it's sort of half technical and half, personality or personal, like sort of figuring out what it is that they want to hear, what their levers really are. And then there's also a prof at the University of Regina who's doing a lot of surveys of people in Regina too, and their sort of willingness to do things like install solar panels or drive EVs or what have you. And so that's sort of coming into it too, in terms of informing some of the scenarios that we're running and how we're thinking about some of the results. So I guess on paper, it's a 3-year project. It's funded for 3 years, and we're about halfway through at this point.
And so in BC, we have lots of great subsidies to go from gas to heat pump or gas to electric. are such things available there, or and maybe you have some results of the surveys? How willing are people to move? I don't know. This is to these new technologies, just from a building perspective. That's my side. So.
Yeah, I'm not really sure if those things were addressed in the surveys, but I know there was a survey about like how willing people were to have different renewables installed. So I asked people, how willing are you to put solar on your roof? And then as well, that question I think was asked with different pricing scenarios. So like, for example, would you do it if it was free? Would you do it if you had to pay? Would you do it if you actually got paid based on the energy that your solar was generating? And I know we also asked people about their willingness to have a wind farm. But I don't, as far as I know, like there's been some interest in terms of like, we've gone to meetings and some of the people who are more on the policy side have asked specifically, oh, like, can you model like ground source heat pumps, for example? But I don't know if like buildings were specifically like a big focus of the survey. I can actually send you the survey. I'll find it and send it in the chat here in a minute. I think it's published, and so you could take a look and see if it says anything about
Very cool.
Yeah.
I think it's interesting to ask, like, do you want to put solar panels on your roof? It seems like a no-brainer. If you make money, yes, of course. Why not?
Yeah.
Well, the question was also, how much more would you pay? Like, what is your
Yeah.
sort of willingness to pay? And this is where the energy, again, coming back to the multi-model thing, this is where the multi-model energies, I think, projects really come in, because it's like, if you know the willingness to pay, then you can model that subsidy. You can look at the uptake, and then you can put that into a building system model or a power system model.
Yeah, I just put the link to the report in the chat. And kind of like to continue on Madeleine's point about how it's really about like how much people are willing to pay. So Brett, the guy who did the survey, he's an economist. And so I think it's really looking, like as Madeleine said, about like, not only are you willing to do this, but like at what price point are you willing to do it? And also like, at what price point does it become too expensive that you would no longer consider it?
Actually, it's funny, Theo, that you mentioned the heat pump subsidy here in BC, because I actually just this morning got my quote for the heat pump for my house here. I actually haven't, but it's an $8,000 subsidy available to me right now. But it's still, a heat pump for my house was about $16,000. So it's about $8,000 even with it, which it's an interesting one, right? Like it's a really interesting, and then it's an interesting, like my furnace is still totally fine. It's got lots of years left. So, and then it's also interesting because what I hear about what's going on right now with Clean BC and City of Victoria is that Clean BC is nowhere near hitting its targets in terms of heat pumps. And so this subsidy, it's a little bit backwards, right? Like this subsidy can only go up. So it's like, do you take the $8,000 now, or do you wait and take potentially 10 grand in 6 months? 12
Oh wow, yeah.
You're
gamifying the whole situation. We should also have a gambling
model for
consumer model on the other end.
But we do, right? Like we know these models, like we have these models, and we can see that we know what they get. We know what those Clean BC, we know what that wedge is in Clean BC, and we know where we're at with that, and we're nowhere near. So if you're a policymaker sitting in the government of BC and you've got this wedge to close with heat pumps and the subsidy's not cutting it, like what are you gonna do?
Yeah, and I think you're overestimating the money they have. You said, what if Victoria has 10 million? Well, it's more like, what if Victoria has $10,000? Like that's more like the amount of money they have to spend on the kind of stuff.
I mean, federally, it's like they just announced $1 billion.
Oh yeah.
Oh wow.
Right?
Is that going to trickle down to Victoria and they're going to be able to distribute it?
I don't know. Well, I mean, their eligibility of those projects is kind of like all over the map. It's mostly for, they just, so I don't know. I don't know how that is going to trickle down, but.
I do like this this is also something I've been thinking about, maybe doing a simple linear model to figure out what is the, because I have a simple stock model of Victoria. So I'm kind of thinking, okay, at what point do these subsidies start matter? You know, at what point do they really start making money for people? And probably that heat pump, it's going to be there for, let's say, 15 years without too much maintenance. And what's your energy bill for your current system? And then cut that by 70%, I would say, probably, given whatever the heat pump will do. I don't know.
No, I had the energy audit. My annual costs are going to be about the same. What I pay for natural gas will be about what I pay for electricity.
Right.
And my natural gas system now is 2016. So we're throwing out a furnace that's got at least another 2
Okay,
years.
yeah. For you, probably it's better to keep your natural gas boiler.
Yes and no, except for that, like, what else can I do? You know, like in my mind, sitting here, I can drive a Tesla, but I don't drive. Yeah. So get off my bike and start driving a Tesla. Okay, well, that doesn't make like a ton of
no, that doesn't work.
Stop flying. Well, COVID took care of that. So it's like
right.
A heat pump is my last. I already don't eat a lot of meat. So it's like, that's my last lever. Talk about levers, right?
Well, we can increase our efforts to make other people make better decisions. That's the way I see it. Because I'm also pretty much like, yeah, what do I have? I don't even have a car. So, you know, there's very little I can do to kind of like, change my diet. But, you know, I don't really eat that much meat either, you know, so yeah, but then, you know, one thing I found interesting, there was a study that came out after the whole COVID came, and it was, okay, COVID basically impacted 5% or something of our global emissions. So where are the other emissions happening? Is this because other parts of the world are not impacted by COVID at that point, maybe? Or are there certain processes? Yeah. Are there certain processes that we're passively engaging with that we're not actively pursuing to like make carbon negative? Like what are those industries, right? So that's kind of that was my big question at the time. I don't know, maybe you have a better idea. Is, you know, our grid in BC is like green because we're mostly hydro. So, okay, then maybe it's Alberta mostly in Canada. So should we all move to Alberta and work really hard in Alberta to make it green there? Maybe we should do that. Let's all go to Alberta. Vote for the Green Party.
I actually have a related question, maybe for each of you, for this, but like the Regina project is really cool in the sense that you're kind of working directly with the decision makers. But since it's one city in Canada, and there's way more jurisdictions, like where do you see the distinction of the work for academia stopping and the kind of repeatability of a consultant or someone kind of taking it on and continuing it and pumping out those reports that are going to be needed for every single city, for example? And I think Theo mentioned it in a previous question or in a previous panel this week, but like where does kind of our work stop and get turned over to those type of people who are going to be kind of doing the day-to-day in-between person between the decision maker and the scientists or the modelers?
Yeah, that's a really good question, and I don't fully have an answer, except for that the sort of privilege that I really see us having in academia is this thing about open access, you know, and this is sort of the problem for a lot of consultants, is they don't want to give up their data and they don't want to give up their models, right? It's kind of the bread and butter. It's how they make money. And so when it comes to that thing of transparency and reproducibility, like I'm just so adamant about open sourcing being a huge element of making this successful. Other people have to come in and be able to look at your code, repeat what you've done, change assumptions and rerun scenarios, so on and so forth. And so anytime you have a proprietary model where you can't do that, or proprietary data where you can't do that. Like, I don't know. I have a hard time with that.
Yeah, I've also thought about this, and Jacob, I think we've actually chatted about this as well, but one kind of different field that comes to mind with modeling is in water distribution systems. There's kind of like a standardized model, EPA net. It's developed and open licensed for free by the EPA a long time ago, and it's what everyone uses. And is there kind of a one to make a robust open access model? Might actually see it being used by consultants who will probably use open access software or tools if they're robust and can provide like what they need. And I think this is also common in other, like if you look at stormwater modeling or some other civil engineering things that rely on modeling, they're often based on something that is open sourced.
Mm-hmm. Yeah, for sure. And I think we could, I mean, I think there's no like theoretical barrier to doing that. I think a lot of the, at least in the States and in a lot of the utilities, like Plexus is the big power system model. And that's a commercial model, and you can't look at that code, use that model and look at that code, but it does drive a lot of, I mean, like that's the end model that NREL uses, for example, right? Or even MISO, the utility, the system operator in the Midwest in the States uses Plexus. So it's like, yeah. And that's kind of, I mean, the big joke at NREL was like, you'd be getting these infeasibilities and it was like, it's for some reason, it's a mixed integer model, and for some reason it can just solve really fast. And so this is somehow Energy Exemplar's secret sauce with Plexus. And the big joke was just that it's not actually solving that fast. They're just throwing you infeasibilities. They're running it in the background and they're throwing you infeasibilities until eventually it solves. And then they're like, oh, you solved your infeasibility. Here you go. Here's your result, sort of thing. But it's like, that's how black box it is. Like, that's how
interesting. Yeah.
And
yeah, can we chat about that for a minute too, and just talk about the base of open source and really the philosophy here? I mean, like, why do you want to use it? Why do academics want to use it? And why would people in general public want to use it? All right. Well, first of all, you could think that you can trust it, right? But in reality, what's so great about the open source is you're showing all of the DNA publicly to everyone, which means that everyone can now question that code, right? So my idea, and where consultants fit in and making their own proprietary software, is for them to use the kernel of the open source so that we understand what they're using, right? There's never any guarantee once they go into that black box and they start adding a little bit more proprietary software. But knowing that it can be based on something that can be validated and verified, right, makes us a little bit easier to accept what they're giving to us. Again, never perfect, right? But this open source philosophy is the idea that we can not necessarily perfect, but we can prod it and we can push it and we can manipulate it until we get exactly what we want. And again, for meeting societal needs, right, we need to do that. If we can't see the operations, then there's not much that we can do with it. So yeah, there should, and kind of speaking to the EPA net, I mean, that was leveling the playing field for those in the water distribution industry, right? They have a common protocol to use now, and they have a common protocol to communicate with. And again, there are many proprietary softwares that have been built on top of the EPA net. But again, just alluding to this idea that if we can at least trust the base level, that will give us a little bit, it'll give us a little bit more motivation and confidence in maybe communicating with those consultants that may use that proprietary software.
And reproducibility too, right? Like, this is one of the things that drives me nuts about, like, here we are publishing in science journals, results that, and I think in other fields, like, and I think energy systems modeling is like a decade behind water system modeling in terms of not actually putting out there what it would take to reproduce our results, right? Like, we publish these modeling papers without any of the data, models, anything that would take for a peer reviewer to actually, or for anybody to actually reproduce our results. Like, it's so against the one of the like founding principles of science, more or less, you know, like and I think that that's, even if, you know, in terms of catching results and fostering trust, but also in terms of having buy-in and things like that. Like if, you know, I put something out there and you disagree with my assumption around nuclear costs, and you can change just that cost and rerun the whole model and get your own answer that now you believe in because it's based on your projection for nuclear costs. That's so much more powerful as a platform for moving a conversation forward than just, I mean, it's just happened. I feel like it just happens all the time where you do this whole study and then somebody comes back and says, oh, but I disagree on your nuclear costs. And then the whole thing gets thrown out, right? Instead of being like, oh, I'm going to change your nuclear costs because I disagree with you on that, you know, assumption, and then rerunning it and coming up with results that you actually do stand behind because they reflect how you think about the world.
Yeah, absolutely.
Mm-hmm. Yeah, that's really interesting. And yeah, no, I see that. Like, I see that as definitely the dialogue where you go back and forth, like, and making sure that the people doing the modeling are on the same page as the decision makers is very important, but it's also very time consuming.
Mm-hmm.
And at some point, research groups can't just keep doing it. They need to keep.
Is that Joel?
Yeah, I think Joel maybe had kind of timed out there for a minute. I mean, I can just add my own point here, is just really alluding to the efficiency that you have, right? If someone makes a call about a particular parameter that you're using your model, it's great to know that we're all using the same model, right? And that we don't have two competing models. And all right, well, now we got to take another 20 minutes to talk about the formulation of your model, just to talk about the difference in a nuclear price, right?
Yeah.
We don't have time for that.
Yeah, in 20 minutes. I mean, like, wow, if you can explain your model formulation in 20 minutes, like, you're a really good communicator. Yeah, and I think not being able to break that down, and often we don't even know, right? Like, often for our own models, we run these different scenarios, and it takes a long time to figure out why scenario A came up with such a different answer than scenario B. Was it nuclear, or was it your storage costs, or was it actually that you turned that constraint off or relaxed your mixed integer, you know, your optimization? Like, who knows? Like, it's just a million things going on, right?
Yeah, too many gadgets sometimes, too many gadgets, and too many cooks in the kitchen.
Yeah.
So. Yeah,
or just a way to keep track of it all, right? Like a way to be like, okay, this model took in all of the same parameter, all of the same assumptions, all of the same input data as this model, and came up with two different results. And so now we know this is down to the model formulation, not your assumption on nuclear, because they both use the same assumption for nuclear.
Absolutely.
Anyway, I'm gonna have to also drop off here. Thanks for coordinating this, Jake.
Yeah, no problem at all. Thank you for organizing this fantastic panel discussion today, and really just kind of showing everybody that what we've been working on. And I think I feel like everyone kind of gets the gist of what we're doing here and understanding sort of the grand nature of this project. So thank you, Madeleine. Thank you to the rest of the panelists that have helped with this today, and for all of our participants that have come today. And you've really made this conference really fantastic. You know, really great that we're into the 4th day. We have one more day to go, and that will conclude everything. But again, thank you so much to everyone who's been a part of this. If it weren't for you, we wouldn't have a conference.
Jake, and if it weren't for you, we wouldn't have a conference either. That's for sure.
Thank you so much. Thank you so much. It's my pleasure.
Take care.